Hi dear students, welcome to today's online class. Today we discuss about crystal systems. In the previous classes we have made some basic idea about crystallography, the terms involved. See, we have learned that in molecular symmetry, based on the symmetry elements present in the molecule, molecules can be divided into various point groups. Similar to that, crystals are also characterized by the symmetry elements present in them. So based on the number of symmetry elements present in a crystal, crystals are divided into various point groups, that is called crystallographic point groups. Actually, there are 32 crystallographic point groups altogether. That is based on the shape, based on the symmetry elements present. Crystals fall under 32 different crystallographic point groups. Now, based on the essential or minimum symmetry present, these 32 crystallographic point groups are again further grouped into just 7 crystal systems or crystal habits. That is what we discuss here. So what are the important 7 crystal systems? Each crystal system or crystal shape indicate, or it is characterized by 2 parameters, what we discussed in the previous class. The crystal lattice, which represent the arrangement of the constituent particles in crystal, is characterized by 2 parameters. Which are they? The axial distance ratio, that is ABC, and axial angle ratio, that is alpha, beta, gamma. So based on that, we can classify, we can understand the 7 crystal systems. Here you can see that the first one, cubic, is the most symmetric crystal system, because A equal B equal C, alpha equal beta equal gamma equal 90 degree. This is the model. This is a cubic crystal system, and you can see all the sides are equal, right? A equal B equal C, and the angles are all equal, that's equal to 90. And the last one, you see, triclinic. This is the most unsymmetric crystal system, because A not equal B not equal C, alpha not equal beta not equal gamma, all are unequal. So crystals can be most symmetric like cubic and least symmetric like triclinic. We can easily compare these 7 and understand and memorize these very easily. Let's go to the discussion of crystal systems. The first one, cubic system. All are equal. An example, sodium chloride, zinc sulfide, etc. Remember that in the present module, we will be discussing mostly about cubic system further in the remaining classes. The second one, tetragonal. See what's the difference. This remains same. Okay, and A equal B not equal C. What happens? 2 sides are equal and 1 is unequal, angles are same. It is something like this shape. See, you can see 2 sides are equal and 1 is unequal. A equal B not equal C. Angles are all 90. That is the shape of tetragonal crystal. Examples are tin oxide and titanium dioxide. And then third one is orthorhombic. Here now A equal B not equal C. Now it is A not equal B not equal C. All the sides are not equal. It is something like this, something like a matchbox, See, all the sides are unequal. If this is A, this is B, and this is C. All are unequal, but angles are all same. Example, rhombic sulfur. Sulfur has got two allotropes. One is rhombic sulfur, which has the shape, orthorhombic crystal shape, and barium sulfate. The next is rhombohedral. See, now we come back to A equal B equal C. Right? These are again same. And now in the angle, all alpha equal beta equal gamma, similar to this but not equal 90. All angles are same but not equal 90. So the crystallographic axis can be taken in different ways, not necessarily like the Cartesian coordinates where it is always 90. Here it is not equal 90. This shape, rhombohedral. Example, arsenic, antimony, sodium nitrate, etc. Then next one is hexagonal. Here A equal B not equal C, like this. Angle is but A equal B not alpha equal beta not equal gamma. It is actually alpha equal beta is 90 and gamma is 120. That's the shape of hexagonal crystal. Example is carbon graphite. You know, graphite has got hexagonal layered structure where you can see this hexagonal unit cells or lattice. Cadmium sulfide. And then next is monoclinic. All axial intercepts are unequal. A not equal, B not equal, C. Angle is alpha equal gamma not equal beta. This is monoclinic sulfur, the other allotrope of sulfur, and calcium sulfate 2H2O. And finally it is triclinic, the least symmetric crystal system. All are unequal. It's very easy to remember. An example is copper sulfate 5H2O, potassium dichromate, etc. So these are the 7 crystal systems. Now, next is about, so there are 7 crystal systems, there are 32 crystallographic point groups. Now, what is Bravais lattice? The scientist Bravais studied about how the lattices can be drawn. What is lattice or crystal lattice or space lattice? It is an arrangement of regular repeating arrangement of points in space which represent how the particles are arranged in a crystal. So if you take a 2D arrangement of points, see the points represent the occupation of particles, right? For example, here in this cubic system, this is a cubic lattice in the sense these points represent the occupation of particles, right? Now in 2D, in two-dimensional arrangement, if you arrange points in all possible ways, Bravais has shown that there can be 5 different arrangement of lattices, 2D lattices. See, a lattice is characterized by the number of neighbors around each particle will remain same. That's called coordination number. That is the peculiarity of a lattice. A lattice is characterized by the coordination number. That means the number of immediate neighbors around each points, each particle which remain throughout the crystal, throughout the lattice, which will be same throughout the lattice. That is the regularity of arrangement. Okay. When it comes to 3D, that is our discussion. We are discussing about 3D arrangements in crystals. In 3D, Bravais has proved that there can be 14 different arrangement of points. That is called 14 Bravais lattices, right? So, which are these lattices? We can see that in the 7 crystal systems, if we note the different Bravais lattices, that I will tell you here. See, in a lattice, suppose it is 2D lattice, suppose a lattice can be it can come in 2 ways. I am just showing a 2D lattice here, okay. Now suppose this is a 2D lattice, repetition of points where the particles are arranged. I can consider a unit lattice or unit cell here like this. This is a square lattice which repeats. You can see the repetition of this lattice along the 2 axes. This is called primitive lattice, where There are two types of lattices. One is called primitive and the other is called centered. Centered. Primitive lattice means there will be lattice points only at the corners. So there are 4 corners here in the square lattice. You can continue drawing the square and develop the lattice, the whole lattice. That's a 2D lattice. This is a primitive lattice. Okay. Now what is a centered lattice? I am taking the same lattice and I can draw the unit lattice or unit cell in another way. Look at this. I am drawing a lattice, a square lattice, but in a different way. What is the difference here? Here the square lattice has an additional point inside. This is called centered lattice. That means there are lattice points in addition to the corners inside the unit cell, or there are some points inside. That is called centered lattice. Okay. Now, when we come to the 3D lattices, it can be of 4 types. One is primitive, we represent by the letter P. That is primitive. The lattice can be primitive. As I said, it can be only at the corners. That is represented by P. Another is body-centered lattice. Body-centered lattice is represented by I, or inner-centered in that sense, I. Then face-centered lattice can be there. There is another Bravais lattice which is represented by the letter F, and rarely there is another one, end-centered lattice, that is represented by the letter C. So there are 4 different types of Bravais lattices. One is the primitive lattice and other 3 are centered lattices. Keep that in mind. Now, how come this 14 Bravais lattices? We can note it here. In cubic, there are the 3 types of cubic lattices. That is, it can be primitive and there is body-centered lattice as well as face-centered lattice. There are 3 types. Then, in the case of tetragonal, there is primitive lattice as well as body-centered lattice. In the case of orthorhombic, all the 4 types are there. There is orthorhombic primitive, orthorhombic body-centered, orthorhombic face-centered, orthorhombic end-centered. And then rhombohedral is only primitive lattice is present. Hexagonal is also only primitive lattice. And then in the case of monoclinic, there is primitive lattice as well as end-centered lattice. And in triclinic also there is only primitive. Primitive is possible for all, of course, and centered lattice is what varies. Now what is the total number? 3 plus 2, 5 plus 4, 9, 10, 11, 12, 13, 14. That is how these 14 Bravais lattices come. Now, our discussion will be more concentrated on cubic system, right? That is what we have to learn in detail. The different types of cubic system. Cubic system is of 3 types. You know, there are 3 possible Bravais lattices for cubic system. Okay. So, cubic system or cubic lattices are of 3 types. That is cubic, primitive cubic or cubic P, then body-centered cubic, that is cubic I, face-centered cubic, that is cubic F. Okay. In common usage, we call them like symbol cubic, body-centered cubic and face-centered cubic. You might be knowing this from 12th standard. You might have learned this. Let us understand in detail about these 3 types. How we draw and how we represent. Very simple, you know. In symbol cubic, let me draw the cubic lattice, the cubic crystal, and show the lattice point. See, there are two ways of representing a lattice or the crystal. See, what is this? This is a simple cubic, correct? Because there are points only at the 8 corners. See, this here we are giving emphasis to the cubic shape and showing the particle as a point. The actual state of affair is that these particles, if this is a lattice point, it is at this point the particle is occupied. So if we show the particle in the real manner, actually this is big enough such that the adjacent particles will be touching each other. So all these 8 particles, if they're shown big, they'll be touching. And this is a model to it. Look at this. This is again the same thing. The cubic crystal, cubic lattice. What's the difference? Here we are showing the particle as it is so that they are touching. Okay. You can see 8 particles at the corners of the cube. And if you draw the cube, it will be like joining the center of all the spheres, right? If you join the center of all the 8 spheres, you get a cube and it will be looking like this, right? So you should have 2 impressions. That is called space filling model. And this is referring to the crystal geometry, the cubic shape, and showing the lattice points. Okay. Now, coming to the simple cubic, let me show the particles. There are particles at the corners. You can show them as the particles small to appreciate the cubic shape, or if you draw them big, they'll be touching. No problems. You understand how it is. Then body-centered cubic is, it's a centered lattice, right? What is the difference here? There are 8 particles at the corners always. In addition, there's an additional point or particle at the center of the whole cube. Suppose your room is a cube. There are 8 corners, as I said in the previous class. Particles are there and there is a particle at the center of your room like this. Then the third one is face-centered cubic. That is coming like this. Where are the additional particles? Here. See, there are particles at 8 corners as usual. Additionally, there are particles at the face center. Center of each faces. How many faces for a cube? I have told you. You can easily understand. 1, 2, 3, 4, 5, 6 faces. The center of all faces. So one is here. The surrounding face, let us go first. Second face, third face, fourth face. Now one face is near to us. This one which will be shown somewhere here near to this corner. And the other is the back face or the rear face which will appear somewhere here. That depends on how you draw the cube. It can be, anyway, it should be that particles are shown at the center of each 6 faces. This is face-centered cubic. Let me show the models for this. I have already shown this is the cubic, symbol cubic, primitive cubic. In BCC there will be an additional particle where at the center of the cube. In FCC there will be particle at the center of all the 6 faces. That means 1 here, 2, 3, 4, 5 and 6. Now if we see them in this space filling model, this is the simple cubic. In BCC, see, it's very important, right? See that in simple cubic, particles are touching along the edge. These 2 are touching along the edge. Okay, that's an important point which we will require later. In BCC, what happens is there will be a particle at the center and it is coming like this, but not like this actually. See, it's very important point. When a particle comes inside, naturally these particles will be opening up, giving space. That means they are not touching. So this is not the actual model. All these 4 particles are pulled apart, right? So that they are not touching along the edge. But particle will be touching along the body diagonal. That means this particle will be touching the centered particle. that will be touching the opposite corner particle. That means in BCC, particles are touching along the body diagonal. That's an important point. Now coming to the last one, FCC. Look at this. This is FCC model. There are 8 corner particles, right? These are the 4 corner particles here, and these are the 4 corner particles here. And there are face-centered particles 1, 2, 3, 4, 5 and 6. This is FCC model. Okay. Now, regarding these 3 types of cubic lattice, we have to understand 4 important points. I will tell it quickly. These are all very familiar points. The first one is coordination number. What is coordination number? The number of particles immediately around each particle in a crystal or in a crystal lattice. So if you take a simple cubic lattice, see, this is only one unit cell. You have to imagine repetition of this unit cell along all the axes. In that case, how many points will be there around each point? It's very simple. You can see that it will be 6. It is 6 here. That is coordination number of primitive cubic is 6. That of body center is 8. That of face center is 12. You can easily get it here from this. One way is that, see, if in primitive cubic, if you consider this particle around it, 1 will be here and just opposite 2. 1 here, 3, and there will be 1 here in the next unit cell, 4, and 5 and 6. In BCC it's very simple. You think about the particle at the center of the particle, center of the cube, and just look around. Around this centered particle, how many particles around? Touching all these 8, right? So that's why it is 8. In FCC it is 12. That you can understand in different ways. One is like this. If you consider one particle, suppose this face-centered particle, for example, you can see these are all touching. 4 in this layer, right? And there will be here 1, 2, 3, 4 touching this side, and there will be 4 this side also. So 3 into 4, 12. See, another point regarding FCC is that in FCC you see that the corner particles are not touching along the edge. They are not touching, just like in BCC, because to occupy the face-centered particle, the corner particles has to get pulled apart, open up. Then how the particles are touching? It's very interesting. In FCC you can see that this is touching this and this is touching this. What is this? This is a phase diagonal, isn't it? See, this is one phase and this is a phase diagonal. So I repeat the point. In primitive cubic, in the actual space filling model, particles are touching along the edge like this. In body centered, like this. Opposite to this one, along this. In face centered, particles are touching along the face diagonal. This is an important point which we will consider later. Now coming to the next point is about Z. What is Z? Effective number of particles. Effective number of particles. Effective number of particles per unit cell. What is it? See, in the primitive cubic, see, if you take a primitive cubic unit cell, all these 8 particles are not belonging to this cubic unit cell fully, correct? Because this corner is shared by many others, right? Actually by 8. If I take this one, see, this is a primitive cubic unit cell. If you repeat this unit cell all over, you can see that this corner is common for 8 cubes, correct? One is this, 2 here, 3, 4 and 4 below. So a corner is shared by 4 cubes or 4 unit cells. That means this particle here, this corner is common to 8 cubes. So what is the share to this cube? 1 by 8. So we have to note that point first before we go into the effective number of particles. That is to be noted. Corner particle, the share from corner particle is 1 by 8. If there is a particle at the face center, suppose, at the face center if there is a particle, for example here, There's a particle, the face center. This is shared by this cube only. So the contribution from face center is how much? It is 1 by 2. And the body center, the contribution from body center, how much? See, body center is well inside the unit cell, it is not shared. So you get the full credit, one particle fully. And one more, there are some Bravais lattice, there is end-centered. If it is end-centered, it will be, of course, like face-centered only. And there is another possibility coming at the edge, edge-centered. If there is a particle at the edge center, suppose there is a particle at this edge, okay, the center of this edge. So this particle is common to this cube and 2 above, correct? 4 cubes will share an edge, that is the point. So the share is 1 by 4. So keeping these points in mind, we can come to the calculation of effective number. In primitive cubic, from one corner, the z value, we are talking about the z value, equal 1 by 8 is one corner and there are 8 corners. So into 8 equals, it is equal to 1, right? So that is the effective number of particles. In BCC, it will be 1 by 8 into 8, that is from the corners, plus there is one body center particle, so it is 2. In face centered, 1 by 8 into 8 plus face center contribution is half. How many faces? Into 6. So what is it total? 1 plus 3, that is 4. So this is important point. Effective number of particles in the different types of cubic lattices. Now next is about packing efficiency, which require this R&A values. This is a work to you, a homework. I am telling you, listen carefully. Packing efficiency indicate how much of the space is occupied by the particle and how much is left free. See, for example, this is a primitive cubic. If you draw the cube, and you can see that there's a lot of empty space inside. So the question is, how much of the space is occupied by the particle itself, which is expressed in percentage. So packing efficiency is given by the equation. You can note that packing efficiency is equal to volume of the spheres present in the unit cell, volume of the spheres by volume of the cube, that is the whole crystal, into 100. Using this equation we can determine packing efficiency of the 3 types. So volume of the sphere or the particles, how we get the volume? We know equation for volume of the sphere is 4 by 3 pi r cube, right? That's the volume of a sphere divided by, what is the volume of the cube? Where you know the edge length A equal C. So if it is A, what is the volume of a cube? It's very simple, it is A cube into 100. Now here, to work it out, if you can substitute R by a relation containing A can get cancelled. That is the point where we make use of this relation between R and A here. See, in the case of primitive cubic, see, if this is the radius of the sphere R, this is also R. So, and you know this is the edge length A. So what is the relation between R and A in primitive cubic? Because the particles are touching along the edge, we can say that A is equal to 2R, correct? A is equal to 2R. So we can get R is equal to A by 2. So substitute it here. And again, one point is, when you go for packing efficiency, you should see how many spheres are there in this unit cell. In primitive cubic, that is the Z value. In primitive cubic, there is only one sphere. So we have to multiply this by Z. That is volume of one sphere into number of spheres. In primitive cubic, there is effectively one sphere in this unit cell. In BCC, there are 2. So Z will vary. Okay. And here Z is 4. That's how it varies. Now, coming to the relation between R and A in the case of BCC, how it comes? Or let's go to FCC first. You can see the particles are touching along the face diagonal, and let me mark it. This is R, this is 2R, and this is R. So what is it? The relation is 4R is equal to what? This one. This is a body diagonal. What is the body diagonal of a cube? You get it from mathematics. If this is A and this is also A, the edges, we know by Pythagoras we can get this what? This is equal to root of A square plus A square, or root of 2A square, or it becomes root 2A. That is the face diagonal. Okay. So using this we can substitute it here, or can be substituted in terms of A. Finally, coming to BCC. In BCC you can see particles are touching along the body diagonal, correct? Body diagonal. This is what is body diagonal. So it is 4R again. 4R is equal to what? The body diagonal of the cube. How you get body diagonal of a cube? If this is A, this is the face diagonal, that is root 2A, which we got it here. And you consider this triangle now. Look, you consider this triangle now, right? This triangle. So A is here, root 2A is here, and this is 90 degree. Again Pythagoras. What you get? This is equal to, you will get it as easily as root 3A. Root of the square of this and square of this. Of course it comes to root 3A. That means the body diagonal of a cube is root 3A. So these relations can be put in this equation and work out packing efficiency. I am just giving the answers and you have to get it out. You have to work it out. The packing efficiency of primitive cubic lattice is equal to 52.3%. That of BCC is equal to 68%, and that of FCC is the maximum 74%. So what does it indicate? Most efficient packing is FCC. Of course, it's very clear. Maximum space is utilized in FCC. Most efficient packing. In BCC 68, more empty space will be there. In primitive cubic, of course, it is least efficient. Maximum space, only 52.3%. So get these values by working out this equation for all the three cases. A lot of points we have discussed in this class. We can see that if a metal is in BCC, it will be, density will be less. If you see D-block metals, you can see they are very dense. Why? Because they are all coming in mostly in FCC arrangement. Maximum space is utilized, so it will have more density, because density is mass by volume. Okay, so that's about the three types of cubic lattices.